Hi, so we're ready to start in Chapter 3, which is numerically summarizing data. The first section, 3.1, we're going to look at measures of central tendency. So we have four objectives. We want to determine the arithmetic mean of a variable from raw data, determine the median of a variable from raw data, explain what it means for a statistic to be resistant, then lastly, determine the mode of a variable from raw data. All right, so let's look at the first objective. So you can see here on the screen is a definition of an arithmetic mean and also the population arithmetic mean, pronounced mu, and the sample arithmetic mean, pronounced x bar. All right, so you can read over those. And we say arithmetic mean instead of just mean because there are different types of mean, of finding averages, but this is one the most common way, and maybe you've never seen the other ways, like a geometric mean and things. So we'll just focus on arithmetic mean, and when we say mean in this class, that's what we're going to refer to. Right? So if you've taken some other classes, you might have looked at some other types of means. So here is just showing the equations for how to calculate a population mean and a sample mean. So some things that you want to note are, right, so this U symbol, right, that's a Greek letter. And this is telling us that it's the population mean. Right, so you're taking the mean of a population, right? And remember, when we use capital N, that tells us the number of observations that are in the population. Where if you use a lowercase n, that's for a sample, right? So this is for a population, capital N, and little n is from a sample, right? And so this calculation, this mu, right? Remember, we refer to this is called a parameter, right? So a parameter is a measurement from the population, where this guy x bar would be called a statistic, right? So you can see here, if we have a list of everything in the population, this is how we can calculate the population mean. And then if we take a sample from that, we can calculate the sample mean. And you'll notice it's done in the same way, right? So for mu, we're taking x1, x2, all the way up to x sub capital N, adding them all together, right? And something to denote is that these numbers here is not a mathematical operation, right? This isn't like like x squared or something. So that subscript is referring to a data value, right? So in other words, x sub 1 is just like my first number, right? X sub 2 is like my second number, and then x sub n would be my last number, right? In the data set, because I have capital N things. So you're going to add up all the numbers together and then divide by capital N, right? And then this fancy notation, this E-looking thing, right? It looks like this, right? This is called sigma. And it literally means, like to sum, right? When you see that in mathematics, right? So a shorthand way to write x1 plus x2 plus dot x to the n, you can just write that as sigma x sub I, right? Where I is going to change, right? So like I could be equal to 1, 2, 3, 4, all the way up to we get to capital N, right? So that I is just going to keep fluctuating. We're going to add all those up and then divide by capital N, which is how many things that we have, right? And then the same thing would be true for the sample mean, at calculating x bar, right? So notice, x sub 1 would be my first number that I have, x sub 2 would be the second, and then all the way up to x sub n, little n, would be adding up all the data values and then dividing by n, right? And then we can use this sigma notation, just like I described above, meaning the same thing, right? So so it might seem kind of weird to see, but sigma notation is really helpful and just an easy way to write that. And we're also going to need it, sigma notation, in the next section when we deal with calculating like standard deviation, right? So sigma just means to add, right? So here's just a few notes, right, that I already mentioned, right? So like just to reiterate, the capital N is going to represent the size of the population, where little n represents the size of the sample. The symbol sigma, right, the Greek letter capital sigma, tells us to add the terms, and then the subscript I shows that the various values are distinct and does not serve as a mathematical operation, right? So distinct, meaning these are like unique. Well, not even necessarily unique, right? But these are like different objects, right? But it's not a mathematical operation, right? Just as I described, right? Because if I have like x squared, right, that refers to x times x, right? That's an operation. But if I have like x sub 2, that's just talking about a specific x value, right? So maybe, for example, when you looked at slope before, you might have seen something like, you have 0.1 where you have x1 and y1, and 0.2 which is x2, y2. So in this case, the subscripts, the 1s and 2s, correlate with the point that you're talking about, right? So then the slope, would be the change in y over change in x, which is y2 minus y1 all over x2 minus x1. Right, so maybe you've seen subscripts before, right? That's all that's meaning, right? It's just to show that things are distinct, right? So what I have now is I have an example of calculating population mean and then also sample mean. So we want to compute the population mean of this data, right? So here's my data set, and this, we could label as x1, this is x2, x3, x4, x sub 5, right, x6, and x7, right? So if you're reading over this, right, it says the following data represents the travel times in minutes to work for all 7 employees of a startup web development company, right? So in other words, this is the times for everybody. So this is a population, right? So in other words, capital N is going to equal 7, right? I have 7 things in the total population. And then part B, we're going to take a simple random sample of 3 employees and work with that, right? So to compute the population mean of this data, right, we're trying to find mu, right, which is the population mean. This is found by adding up all the x's, x sub i's, and dividing by capital N, right? So I can write this out just to iterate what this means, right? This means I'm going to take x1 plus x2 plus x3 plus x4 plus x5 plus x6 plus x7, and then divide by capital N, which is 7 in this case, right? So this would be equal to 23 plus 36 plus 23. So I'm just filling in those data values for x sub I, 23, and then we have 18 plus 5 plus 26 plus 43, and then all divided by 7, right? So we need a fault order operation. So if you total the top here, you should get 174, and then I can divide that by 7, right? And then so this comes out to be approximately 24.86, right? And something that you want to note is when you're working with mean, you know, your units here are minutes in your data. So when you calculate the mean, the units stay the same, right? So this would also be minutes, right? So this is like an average, a typical time, right? So then the next thing that we want to do is to take a simple random sample of 3 employees from that data set and calculate the sample mean, right? So there's a couple of ways that you can do this. So I'll open up Statcrunch. Right? And I could just type in these values. We have 23, 36, 23, 18, 5, 26, 43. Right? And we could double check ourselves. So if I go to stat and then summary stats and do column, I can actually find some summary steps for variable 1. So I can hit compute and we get that, right? So you can see there's a lot of different things here, but the mean value is what we were after. Which was 24.86, which is what we found here, right? Rounded. So then what we're trying to do is to get a simple random sample. So if you remember, what I could do is I could go to, I believe this was data and then simulate and then discrete uniform, right? So really we only need three numbers, but I'm going to put in like 10 because remember with Statcrunch it's possible that we could get repeat numbers and we don't want to have with replacement in this case, right? So we just want one column. The minimum number we want is 1, the max is 7, and I can hit compute. And then so here's a list of random numbers, right? So I got 2 and then 2 7, so I only want one of them, so I'll skip 1 and then 5, right? So in other words, from doing this with random numbers, right? So my sample 1, my random numbers that I had gotten were 2, 7, 5. Right? So then what that tells me is I want to find the mean, right? The sample mean using x sub 2, x sub 7, and x sub 5, right? Because essentially what we did is the subscripts, we just let those be the numbers for each thing. So then I found a set of random numbers, randomly picking 3 from 1 through 7 and got these numbers, right? So in other words, we want to find x bar for this, right? So what we're going to do is take x sub 2 plus x sub 7 plus x sub 5 and divide by 3, right? Because I want to have n equals 3. Because x bar is equal to the sum of the x sub i's divided by little n, right? So we're only considering these 3 things, these 3 values. So then now I just need to fill in those values. So x sub 2 is 36, x sub 7 is 43, and then x sub 5 is 5, and then divide by 3, right, and then I can get that mean. Right, so 36 plus 43 plus 5 is 84. I want to divide that by 3. And I get, that's exactly 28. Right? So that was one sample. So we need to get a second sample. I'm running out of space here, so let me scroll over to the side. Right, so we want to get sample number 2. So I need to, get some random numbers again. Right. So if I go back to Statcrunch, I could click in here again and go to data, simulate, discrete uniform. And then I'm just going to throw in 10 numbers again. We want just one column. The minimum number was 1 to 7. And then I'll hit compute. And we got some additional random numbers, right? So the first 3 there's no duplicates, right? So you would just use all of those. So we have 3, 7, 2, right? So I would go back to OneNote. My random numbers are 3, 7, 2. So in other words, x sub bar, right, is going to be equal to the sum of the x sub i's divided by little n, right? So these are my only 3 numbers in the set, right, in the sample. So then what I'm going to do is take well those aren't my numbers in the sample, right? What I meant was like x sub 3, x sub 7, x sub 2, right? Those are the only numbers in the sample. Right? So then this would be equal to, taking x sub 3 plus x sub 7 plus x sub 2 all over little n, which in this case is 3. So then x sub 3 from our data set was 23. X sub 7 was 43. And x sub 2 was 36. Right, so then I can add those together and get 102 in the top divided by 3. And we get 34. Right, so for the second sample I got 34, and in the first sample I got, hang on. There we go. Oops. Right, so you can see in the first sample, right, remember we got 28, right? So we got different values by taking 2 different samples, right? Because we had different things in our sample. So that's something to pay attention to that we're going to use throughout the class, right? Is that idea of taking a sample from the population, right? And we're getting different values, and so those are going to vary. They're not always going to be the same, right? So then another thing that we can do is you can actually have Statcrunch build the sample for you, right? So like if I go to data and then sample, I pick the column that I want to take a sample from. So I want to take from variable 1. The sample size that we want is 3, and we want 2 samples, right? 2 of those. And then I can hit compute. And then so here are my 2 samples. So notice I didn't have to use a random number generator because it randomly picked numbers that existed in this column, right? So that's helpful. And then what I could do now is I could just go to stat and then summary stats and do by column. And then I'm going to pick sample 1 and hold down control and hit sample 2. And then I'm just going to select the mean. It's really what I'm interested in, and I can hit compute. And so now I have a mean for each of those samples, right? So and if I wanted to, I could add in variable 1. So I'm going to hold down Control and add in variable 1 into here. And then so this is just like a nice summary table for the means. So we have the 2 sample means here listed in order, and then the very last one that would be the population mean, right? So notice they're not all equal to the population mean, right? That's why we need to use a different symbol for that. All right, so now what we want to do is to use some technology. We want to use a data set called Chicago salaries, right? So there's a couple of ways you can get to this. So let me show you. Right? So if you go to modules and go to the data sets module, I have the Chicago salaries listed here as a CSV file format. You could download that and then copy and paste that into Statcrunch. Or if you go into My Lab and Mastery and then open up a new tab in My Lab, and then you could go to Statcrunch, or you could go to data sets too. I can get you there, but I'm going to go to Statcrunch and click data sets from our textbook, and then we're in chapter 3. If I scroll all the way down, I get the Chicago salary. So if I click on that, it has it downloaded into Statcrunch for me. I don't have to copy and paste, so it's a little easier, right? But keep in mind, it doesn't always work perfectly, like we experienced with the tornadoes data set. Hopefully Pearson's able to get that fixed, but this appears to be working. I was playing around with this earlier, and it seems to be working fine, right? If it doesn't work, don't forget, I always have those backup data sets saved to Canvas, right? So for part A, what we want to do is compute the population mean of this data, right? So this is more realistic. You know, there's a lot of pieces of data here, right? And we have 3 different variables, right? So we have someone's job title, right? So this first person, right? So this is in a stacked data format, right? Where each row is a person. So this first person is a police officer. They work in the police department, and that's their average salary in Chicago, right? Where if I go to the second thing, this is a new person who's a sergeant. They're also a police officer, and they make this salary, $104,628, right? And then you can see row 3, we have a lieutenant EMT. They work for the fire department, and they make this money, right? And then we got staff assistant for the law office, and they make this amount of money, right? So each row is individual person, right? We have 3 different variables. So if we want to calculate the population mean of this data set, you know, this would be very tedious by hand, like not very practical. So that's why it's really important in a stats class to learn how to use a piece of technology like Statcrunch. So if I go to Stat and then Summary Stats and then go to Columns, I can select the variable I want to do summary statistics on, and the only option is annual salary because that's the only, you know, quantitative variable. And then I could click maybe tell me the N and the mean, right? And I can hit compute, right? So that tells me we have 25,159 people in the in this data set, right? That's a lot of people. I would not want to do that by hand. And then it tells me the average salary here, which is 86,793, right? Also, if I go back to options, just open that menu. There's an option here, a statistic called sum. So if I hold down Control and hit sum and hit compute, now it's going to give me the sum of all the data, the n value, and the mean, right? So if I took the sum and divided it by n, that would be equal to the mean, right? But notice the sum is written out as 2.1836267E9, right? So that is how a computer codes what we call scientific notation, right? So, and this will come up multiple times. So let me write out what I mean here. Right. So what we had for the sum was 2.1836267 E9, right? So sometimes you might see this as a lowercase e or a capital E, depending on the software you're using. But that E value is essentially times 10, and then this next number is what goes here as an exponent, right? So this value, you can interpret that as 2.1836267 times 10 to the 9th, right? So that's scientific notation. Right, so we use scientific notation to represent really big numbers or really small numbers, right? It's a convenient place to write it. So if you have times 10 to the positive 9, you're going to move the decimal spot 9 spots to the right. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, 9 times. And then you can fill in these empty spots with zeros, right? And that will give you the number, right? And it's possible, this was rounded, so it might not be an exact value. But we just need to know it's a really big number, right? And if I take the sum and divide it by n, the number of things we have, that's what gives me the mean. All right, so let me fill in some things here. So we found the population mean to be equal to $86,793.64. And remember, when you find the mean, the unit's the same as your data, right? So the units here would be dollars, right? Because that's what our data, the unit for that is in dollars. So when we take the mean of something, we stay in the same unit. So then in part B, what we want to do is take a simple random sample of 15 employees. We want to do this twice and get 2 sample means, right? So I'm going to go back into Statcrunch. Let's see. Oh, here. Over here's where this data was, right? So I want to go to data and go to sample, and I want to get a sample from the annual salary column. The sample size I want to be 15, right? That's what we were told, and I want to get 2 samples, right? And then I'm going to hit compute. So now you can see there's sample 1 and there's sample 2. So what I'm going to do now is go to stat summary stats by column. I want summary stats on the annual salary in each sample, and I want the mean. So I can hit compute, and now I have a nice table for the population mean, what we found in part A, which is this top row, and then the 2 rows below it are my sample means, right? So this sample 1 is from 15 people that were chosen randomly. It's a random sample, and this one is also just another sample, right? And notice that varying that's happening, right? We're not all going to get the same value, but we would expect to get somewhat close to the mean, right? It would be really odd for us to get a sample of 15 people and to only get a sample of like $100 or something, right? So notice that my values are still in the ballpark of the population mean. Right, so we could go back here. So we did this So I'm going to use x bar sub 1 to be for sample 1. So this was $87,140. And for sample 2, we'll use x sub 2 bar, which was $82,411. Or no, these were numbers I got earlier, right? These aren't the numbers that we just got. These are different samples, right? So our first one was actually 89,189.2 and 93,074.4, right? Sorry about that. Right, so those are the two numbers that we got here, right? So if you replicated this with me, you're going to get different values, right? All right, so I think that's enough for mean. So I want to go to the next learning objective, which is on median. So we want to be able to find the median. So you can see the definition: the median of a variable is the value that lies in the middle of the data when arranged in ascending order, right? So we use capital M to denote the median, right? And then it's going to work a little differently depending on if you have an even number of observations or an odd number, right? So I have here listed, steps in finding the meaning of a data set, right? So you can look over that and read over that. But I think it helps to go through this by hand, right? So that way it's a little easier to comprehend. So we have the numbers 23, 36, 23, 18, 5, 26, 43, right? So this is my data set. First thing I want to do is rearrange this so it goes in ascending order, right? Smallest to biggest. So that would be, we would have 5, and then 18, and then 23, and then 23, then 26, then 36, and then 43. Right? So that's in order from smallest to biggest. Now what we're looking for is the middle number, right? So I have, I can kind of check them off in order. So we got one on this side, and one on this side, and then one on this side, and one on this side, until we get down to the middle, right? So this is the middle number, right? Notice we have 50% of the data here and 50% of the data over here, right? So that middle number is what we call the median, right? And so we're going to find the median of two different sets. So I'm going to call this M sub 1. Capital M we use for median. So I'll use capital M sub 1 to mean 23, right? Equals 23, this value here, right? And then something else I want to do is interpret this. Right? So interpretation that I would give for this value, this median value, and we want to do this in context, right? So it's important to understand what these data values, where they came from, and this was this was a data set that we had just worked on the last page, right? So a sample interpretation of this median value is the following. We could say, 50% of the employees of the startup web development company travel more than 23 minutes to work. While 50% travel less than 23 minutes to work. Right? So median is all about finding that middle value, right? So 50% are going to be less than the median, 50% are going to be more. And notice how I put it in context, right? I was, using the language from the background, right? So that's an important skill to be able to do, right? So remember, statistics, a statistic is not just a number; it's a number with context, right? So it's important to know the units, how it was collected, what does the number represent, right? So in this next example, we're essentially doing the same thing, but we're adding in some new employee that we just hired that travels 70 minutes, right? So if we put the data set in order from smallest to biggest, it's going to be in the same order, just with the number 70 at the end, right? So I would have 5, 18, 23, 23, 26, 36, 43, then lastly 70, right? So then same idea, if I cross out one on this side and one on this side and keep doing that until I work my way to the center, what you're going to find is I'm going to have two numbers in the middle. Right, because we have an even number of observations now, where before we had an odd. So when that happens, what you're going to do is average those two middle numbers, right? So the median, in this case, I'm going to use m sub 2, is going to be equal to 23 plus 26 divided by 2, which that's 49 divided by 2, which is 24.5. Right? And then so you could interpret that if you wanted, but you would have a similar interpretation, right? Just a different value for the median. So instead of 23, you'd write 24.5. Right? And you could double check that in Statcrunch if you wanted. So I'm just going to go to Statcrunch and open up a new data table. So in variable 1, I'll just put in our first set of numbers, right? We had 23, 36, 23, 18, 5, 26, 43. And then in the second set of numbers, we had the same numbers and then a 70 added, right? So I'm just going to select this and do Control C, and then click over here, Control V, and then I need to add the number 70 in, right? So then I can go to Stat, Summary Stats, Columns. I'm going to select both of these, variable 1 and variable 2. I'm going to select N, and I'll select median, if I can find it here, right here. Right, and I'll hit Compute, and you'll see for variable 1, the first data set, the median was 23, which was what we found, and there were 7 things in there, right, an odd number. And then in the second set, variable 2, the median was 24.5, and there were 8 objects, an even number of observations, right? So that's a nice, easy way to find that, right? So now we're ready to look at the third concept. Is we're going to investigate what it means for a statistic to be what we call resistant, right? So in parts A and B, we want to calculate the mean travel time for each of these, right? And we actually already did this work for part A. So we did this prior, and what we found is that mu, and I'll say mu sub 1, was equal to, right, so we took the sum of the x sub i's divided by capital N, and we got 174 over 7, and this was approximately 24.857. Right, we found that before. So then in part B, we're doing the same thing, but we're going to add in the number 70, right? So, we would have mu sub 2 is equal to the sum of the x sub i's divided by big N, which this would be equal to 23 plus 36 plus 23 plus 18 plus 5 plus 26 plus 43 plus 70, all divided by 8, right? I have 8 things here. And then so this equals 244 divided by 8, which is 30.5. Right? So we want to compare these two values. So compare the results from parts A and B to the examples in the previous objective. How do the mean and median of travels change with the new employee, right? So what you'll notice is, if we're comparing the means with the new employee, the mean with that one number 70 increased by quite a bit, right? It went from about 25 to 30 minutes, right? Which is pretty significant, right? It's not, super, super different. So what we could say is that, mu sub 1 is less than mu sub 2, right? So, but if we compare the medians, right, from before, so the median was at 23, and now it's at 24.5. So it didn't seem to change as much, right, if you will. So what we could say, right, is that adding the 70, the largest value, pulled the mean higher, right? Pulled it in that direction, right? So notice that adding a number 70 in is a really large value, and it pulls the mean up higher. Where if we put in like a really small value compared to the other values, it would pull the mean lower, like to the left. So it pulls it in that direction of that like extreme value. Right? So where the median was not as impacted, right? In other words, the median sub 1 was approximately equal to the median sub 2, right, from the previous page. Right, so we're just noting that this 24.5 and 23 are about the same, where these seem to be pretty, seems to be impacted more the mean by adding in that one number. Right, so we could say, just adding on here, we could say something like, just one, extreme value, number 70, had a big difference. On the mean, right? So then in this box here, this information, it says a numerical summary of data is said to be resistant if extreme observations, which are very large or very small relative to the data, do not affect its value substantially, right? So a median is resistant, while the mean is not resistant, right? So it's something to note, right? So if I add in some outliers, the mean is not as impacted as, or the median is not as impacted as the mean, right? So median is resistant, while mean is not. All right, so now what I'd like to do is we're going to do some exploration, and there's directions listed here. So I'm going to just use this Statcrunch. So it says to go to applets, and then there's this mean deviation versus median IQR, right? We open this up, and I'm just going to hit compute with what that's listed there, and it gave me some values here. You know, we wanted to have a data set where the median and mean is both roughly equal to 2, right? So if you wanted, you could, you know, like drag and drop these until we get, you know, something to that effect, where we want the mean and the median to both be roughly equal to 2. Right, so you could play around with these. Right, and so that looks like something roughly equal to 1 and 2, right? And then it says to add a point, a new observation at 9, right? So if I click add point and add a new observation at 9, and I hit OK, right? We want to note what happened to the mean versus the median, right? So before, so if I just get rid of this value, right, the mean was 2.157 and the median was 1.98, right? So if we look at that and compare that to adding in the point of 9, what you'll notice is the median stayed roughly the same, but the mean changed, you know, pretty drastically, right? So the median stayed about the same, but the mean got higher, right? And again, it's because I added in this like outlier, this extreme value on the right side, right? So then now what we were asked to do, so 2A, it says to remove the single value near 9, right? So let's get rid of the 9 value. And then we want to add a point and add 24. Right? We want to think about how the mean and median changed, right? So notice the median is still roughly about 2, but the mean is 4.142, right? And remember, originally we had, you know, a mean of roughly 2. So it's almost double. Just that one single value that's different affected the mean a whole bunch, right? So what we want to, you know, just kind of discuss there is that phenomena, right? So those large extreme values have a much bigger impact, just one of them, on the mean than the median. Right? The median is still about 2. It's not as affected. Right? So then now number 3, it says to click reset and then add a point at 0. So add a point at 0. And then it says add a point at 50. Right? And then we're going to remove those points, and all that's doing is getting us a number line from 0 to 50. Right? So then now it says to create a symmetric data set of 6 observations such that the mean and median are roughly 40. Right? So the values that I picked for this are 30, 40, let's see, 3 more 40s. So 130, 4 40s, and then a 50. Right? And this is exactly where the median and the mean and median are both equal to 40 exactly, right? So we wanted to get something that was roughly 40, but I was able to get something that's exactly both of those, right? So that's part A. So then now, or excuse me, that's part B. So now part C, you can see that we're asked to add a single observation at 35, and think about how does this new value affect the mean and the median, right? So if I click add point and hit number 35 and hit OK. Notice the mean and median are not as impacted, right? And the reason why is this 35 number is not an extreme value, right? It's pretty close to the mean already, right? Our mean was 40, our median was 40. So if I add a number that's close to 40, it's not going to really impact the mean and median as much, right? What's going to impact it is if we have a really large or really small number there, right? That, like an extreme value, as we talked about. So now then, part D, it says to grab this new point and drag it, this 35, and drag it over to about 0, and look how look what's impacted. So the median is still at 40 for us, but the mean went from 40 down to less than 35. So again, what's happening is this is an extreme value that's on the left, right? Smaller than the mean, and what's happening is it's pulling the mean down in that direction, right? So then now what we have is we can click reset, and for number 4 it says to add a point at 0, add a second point at 50. So we want to get a number line from 0 to 50 again, and then we're going to add about 25 to 30 points to create a symmetric dot plot such that the values of the median and median are roughly 40, right? So to save time for this, I added in a data set. So if you go to modules, called 3.1 underscore exploration, right? So if you open that up, and I already have that Excel file downloaded on my computer, right? So then notice I have these numbered. So this 4B, this is a data set for 4B, and then 6B1, 6B2, and so forth. These are all data sets we'll use in this exploration activity. So I'm going to copy this, and then I'm just going to open up a new data table in Statcrunch, and I will paste this here, right? So then we still want to use that applet. So the applet mean standard deviation versus median IQR. And what I can do now is I can click data table, and I'm using the column 4B, and now I can hit compute, and what it's going to do is just pull in those numbers that I already had listed, right? So you can see this makes a symmetrical dot plot, and we have the mean and median are both equal to 40 exactly, right? So that's part B. So then part C says add a single observation at 35. How does this affect? So I'm going to add a point. And I'm going to add number 35 on here. I'm going to click OK. And you can see the mean dropped a little bit, but the median was unaffected, right? But really the mean stayed about the same, right? And it's easy to get an understanding for that because I added a value that's near the mean, which was at 40, right? So this value of 35 is not atypical, right? It's not super crazy. And then what I'm asked to do now is drag this. Well, I was asked to drag it down to 0, but I actually just dropped it off, right? So I'm going to click add point, and I'm going to add in the number 0 and see how that impacts things. And notice the mean dropped even more, right? So that one data value at 0 pulled down the mean, in that direction, right? Because that would be, somewhat of an outlier, right? Extreme value. But the median wasn't as impacted, right? Because remember, the median is what we call resistant, while the mean is not resistant, right? So then for number 5, we're gonna write a paragraph to talk about what we just learned. right? So I'm just going to type in type here. So we could say something like, oh, let me make this black font. Right, so we could say something like adding a value near the mean slash median, what we call the typical value, doesn't impact the mean slash median that much, right? But when you add a value that is not near the mean slash median, it's what we call extreme value, the mean goes in that direction. The median is not as impacted by the extreme value. Right, so it's just a sample, some sample sentences that we noticed, right, observed. All right, so now for number 6, we're doing something somewhat similar. So we want to create a data set of at least 10 observations that the mean equals the median. What is the shape of the distribution, right? We want something between 0 and 50 again. So if you go back to Statcrunch, for 6b, this is one example, and this is another example that we'll look at as well, right? So these are my data values, right? That I came up with, and to save time, I'm just giving those to you in this form. So if I go to the applet again and go to this mean deviation, and then I'm going to pick things from the data table. I want 6b1. I'm going to hit compute. So you can see, this is a dot plot, right? You can see the distribution shape, and the mean and the median are both equal to 30, right? And we wanted those two things to be the same. So this looks like a bell shape, right? So you can see with that dot plot, or if you wanted to make a histogram, right, you could go to graph, and then histogram of 6b1 and hit compute. You can see that histogram, it looks to be like a bell-shaped distribution, right? It's symmetrical. Remember, bell-shaped is a symmetrical distribution. And then you could do the same thing looking at 6b, right? So if I go to the applet and then mean deviation, and then I'll select 6b2, hit compute. So here's the dot plot, and you can see that this is a uniform distribution, right, which is also symmetrical. So remember, symmetrical just means you can cut it like in half, and it'll be like a mirror image roughly, right? So the mean and median are equal, like we wanted, and this is a uniform distribution, right? And again, if you wanted, you could go and look at the graph, look at a histogram of 6b2, and you can see that this is a uniform distribution, right? But the key thing here is that they're both symmetric, right? Because it talks us to, tell us about what's the shape of the distribution. What you want to pay attention here is that when you have a symmetrical distribution, that's when your mean is going to equal the median, right, roughly. So then part C, it says to create a data set of at least 10 observations such that the mean is greater than the median. What is the shape of the distribution, right? So that was the 6C data set. So if I go to the applet and go to the mean deviation and select the 6C, hit compute, you can see that the mean is 24.545, the median is 20, and that's what we wanted, right? We wanted wanted something where the mean is bigger than the median, and that looks to be right skewed, right? It looks to be a right skewed shape, right? That long tail's on the right side, right? That's how we remember the right skew. So then we're asked to do the same thing in part D, except we want the mean to be less than the median, right? So if I go back to the applet, the mean standard deviation, and then use the data set that I had given you in labeled it 6D and hit compute, right? Here's an example where the mean is less than the median, and if you look at this shape, it is skewed left, right? Left skew. Right? Right, so just filling these in, right, the big things. So the main thing we wanted to answer here is that this is symmetric, right skew, and left skew. And then parts E and F, we want to have something with 50 things in it, right? So I definitely wanted to use, give you a preset data set for that. So that's 6E and F, 6E and 6F have the 50 number of 50 data sets in it, right? So for part C, we want to create a data set that is skewed left with at least 50 observations. Describe the relationship between the mean and the median, right? So if I go to the applet, the mean standard deviation, and then go to data table, and we want to pick 6E, hit compute. So you can notice by looking at this dot plot that it's definitely going to be skewed left, right? My long tail's on the left side, and I can see that the median is bigger than the mean, right? So in other words, these are kind of like my extreme values down here, and they pulled the mean downward, right, to the left of the median. Right, so if I just edit this and use 6F, right, so I just wanted something that looks like the opposite. I wanted at least 50 observations and look at something that's skewed right, right? And something I didn't point out before, these little triangle things, these are showing where the mean and median are, right? So green is mean, and the red thing is the median, right? And if you hover over it, it tells you those exact values, right? So you can see we have what we wanted here. We wanted a mean bigger than the median, right? So that's skewed right. All right, so if we look down on the notes a little bit, we have this nice table that shows the relationship between mean, median, and the distribution shape. So we have some, in words here that, when we have something that's skewed left, the mean is going to be substantially smaller than the median. If it's symmetric, the mean is going to roughly be equal to the median. And when you have a skewed right distribution, the mean is going to be substantially larger than the median, right? So we have some pictures here to also show that if you're more of a visual learner. So symmetric, the mean and median are about the same. For skewed left, the mean is pulled left, right? So it's the left of the median. And for skewed right, the mean is pulled right. So the mean is to the right of the median, right? So that's important to note, and that's also some rationale to why we use, why we call, this guy skewed right and why we call this one skewed left, right? It has to do with the mean going towards that direction. So that's another way you can help remember that. And then this is just a word of caution you can read over. These are just guidelines and don't always, always work out for everything, right? So we just want to, take those lightly, but that's generally what's going to go on roughly. Right, so then the very last thing we want to look at is calculating the mode. So the mode of a variable over all data. So the mode of a variable is the most frequent observation of the variable that occurs in the data set, right? So to compute the mode, you're going to tally the number of observations that occur for each data value. The data value that occurs the most often is the mode. A set of data can have no mode, one mode, or more than one mode. And if no observation occurs more than once, we say the data has no mode. Right? And then here's just a nice summary of some things that we've been doing. Right? So definitely the interpretation. Right? So a mean is kind of like the center of gravity. It's like a balancing act. The interpretation for a median, where we're dividing the top and bottom 50% of the data, and then here's interpretation, right? Also, when finding the mean, this is good to use when your data set's roughly symmetric, right? So it says that here. Where the median is best to use if you have skewness going on, skewed left or right, right? So we use median for symmetric distributions, and this is if we have skewed distribution, we're going to use median, right? So that's important to remember as well, right? So now what I would like to do is just look at a few examples of calculating mode, right? So I'm just going to give you some data sets. So if I have the numbers 1, 2, 3, 4, 5, then this is going to have no mode to it, right? Because there's not one observation that occurs more than once, right? And then if I have the numbers like 1, 2, 3, 4, 5, notice the number 3 occurs twice and all the other numbers occur once, right? So the mode in this case would be equal to 3. And then the next one, is 1, 2, 2, 3, 3, 4, 5. So in this case, I have the numbers 2 and 3 both occurring twice. So they're actually both going to be the mode, right? So this is a case where you could have more than one mode. So the mode would be both 2 and 3, right? They both occur the same number of times. And then the next example I have is what if we have the data set like 1, 2, 2, and then 3 3s, and then a 4 and a 5. Right, so what I did is had the previous data set and added a number 3. Right? In this case, the mode is going to be equal to 3. Right? And that's because it occurs the most. I have 3 3s, and nothing else occurs 3 or more times. Right? So then my next data set is having the numbers 1 through 5, but all of them having a frequency of 2. Right? So this is a uniform distribution. Right? Everything occurs the same number of times. So for a mode for this, you can actually say that there's no mode, or you could list everything as the mode. Really just depends on the definition that you're using, right? So there's not agreed upon consensus in the statistical mathematical community about what you do in this case when you have like a uniform distribution. So I guess something that you could ask yourself is what's more useful? Is it more useful to list each number once, or to say there's no mode? So personally, I think in this case it's more useful to say that there's no mode, because that tells me that there's not one number that occurs more often than another number, right? And I'll post an article in this section as well underneath the notes that you can read if you'd like. So someone posed this question, this type of question on a website called Ask Dr. Math, right? All right, so I hope this is useful. Let me know if you have any questions. Thanks.